Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's just jump into it because we were in the middle of a problem last time. So there we go. All right. I think that's it. This is 1108, section R05. And let me make sure I can see the chat. Is anybody out there? Anyone on video? Okay, Tommy's here. All right. Stephen. Okay, let's actually, Kathleen, hello. How you guys doing? Hopefully good. Let's get back to it. So last time, put you guys in a couple groups and you had to figure out these things. Sketch the feasible region, find and indicate all corner points, and state whether the feasible region is bounded or unbounded. So yeah, we had 5 examples. I think at least you went through the first 2, but let's actually go through these together. So this was actually the what the picture would look like. Did anyone find the point right here, what that's supposed to be? I mean, it says find all corner points. The other ones are more or less obvious because they occur on the axes. They're actually the intercepts. Yeah, so this one is like 5, 0, that's 6, 0, that's 0, 4, 0, 5. The origin is 1. Well, it would the points that you want to find would depend on the region, I guess. So what was this one? The green dot. You can just tell me. You don't have to like raise your hands or wait on me to call on you or anything. Did anyone find it? Okay. How would you find it? Like I want to find that green dot. What would I do?
Oh wait, never mind. Sorry.
What would I do? Like what would I try to? How would I compute it? Ideas? No idea how we would get to that? I mean, what do you notice about it on the picture?
They intersect?
It intersects, right? Where the blue and red intersect. So what do you think that would mean? What do we want? So the XY coordinates on that green point have to be able to do what?
They have to be plugged into both equations.
Both equations. It has to work in both equations, right? Which means what do we need to do?
Set them equal to each other.
How would you do that?
Put them in y equals mx plus b form?
Okay, so I think you're starting to solve the problem, but what kind of problem are you setting up? I mean, it's the thing I asked you guys to review just before we started 5.1. You'd actually set up a system of equations. Right? You look at the two lines that are intersected, and you want to find the x and y coordinates that work in both. This means it's essentially saying, I want to solve the system of equations that solves both of these. So I need x plus y equals 5. And at the same time, I need 2x plus 3y to be equal to 12. Now, there are going to be a couple ways you could do this. Yes, you could solve both for y, put it in y equals mx plus b form and set those equal to each other and solve for x and then go back and find y. That process is called substitution. And another nice way is called addition or elimination, in which case, say that's equation 1 and equation 2. What we could do is say, multiply equation 1 by -2. Call that equation 3. And then what I can do now is actually just add that to equation 2. And so you'll notice that I have 2x minus 2x, so those are gone. 3y minus 2y, so that leaves me with 1y. And then 12 minus 10, that leaves me with 2. So my y value is 2. And this would mean that my x is 3, yeah, of course, since my x plus y must be 5. So if my y is 2, my x must be 3. And so this is 3, 2. Okay. We're going to need to know how to do that. And we're going to need to know how to do it very quickly. Okay. So that's how you'd find the coordinates. See what lines intersect, set up a system of equations, solve the system of equations. That is how you would find the point. Now we have that point. Okay. And we have this system up here. How do we, what region satisfies that system? So I numbered them for us here with Roman numerals, since I'm already using regular numbers on the axes and labels. So we have region 1, region 2, region 3, region 4, region 5, region 6, region 7, region 8, region 9, region 10. So which of the regions, could be several of them, would need to be shaded in order to answer this problem? So the system is up there. We have 2x plus 3y is less than or equal to 12, x plus y is less than or equal to 5, x greater than or equal to 0, y greater than or equal to 0. What region satisfies, what region or regions satisfy all of those things at the same time?
I think it was 10.
I think it's region 10, as in here.
Yeah.
Anything else? So we can check what that is. So of course, again, multiple ways we could do this. If you plug in the origin into both, you realize that it works. So you can know it would be to the left of both of these lines, or you can look at it as below both of these lines. If you just think of solving for y, you'd end up with y less than or equal to something. And so we know we need to be below both of these lines. So I need to be below the red line. I also need to be below the blue line. I need to be to the right of the y-axis, and I need to be above the x-axis. So I know I'm looking in the first quadrant, and I know I want to be below both lines in the first quadrant. Region 10 is the answer. This is the feasible region. Now, to answer the question of bounded or unbounded, is this a bounded region or an unbounded region?
It's bounded.
Bounded. So remember, bounded means you can have a circle centered at the origin of finite radius that will cover the entire region. It's enclosed, can be enclosed. It doesn't go on forever. So this is actually bounded. All right. So that will be that. Now, moving on to the next one. We know that, of course, this is 3, 2. We slightly modified the system of equations. Now it's greater than or equal to in both. What region do you think solves that? So, I mean, we already did a lot of work in part A. So that should help us with all the other parts. For example, in part A, we know that less than or equal to really meant below both lines. So greater than or equal to would mean pretty much the opposite. You shouldn't have to do any calculations here. What region solves this?
Is it 1?
Region 1, you have to be above both lines, right? So you have to be on top of the blue and on top of the red at the same time. Region 1, bounded or unbounded?
Unbounded.
Unbounded, right? Goes on forever. You can't contain it, right? There's no circle of finite radius that I can center at the origin that will cover everything. It keeps going on forever, right? It keeps going up. Okay, this one. What region solves that? And again, we know that this is 3, 2. Well, what do you think?
Would be region 2.
Region 2. So looking at this, I know I want to be region 2 as in up here.
Yeah.
So I want to be, according to that, below the blue line and above the red line. Does region 2 satisfy that?
No, it does not.
No. So what region?
You said below the blue and above the red, right?
Yeah, I mean, the
So
first
would it be-
equation, the first equation is blue, and the second equation is the red equation.
Okay, so then would it be the
For all of
IX?
these. The
So what is that, 11?
right, that's 9.
9.
Yeah, below the blue, above the red, in the first quadrant. That's the region. Bounded or unbounded?
Bounded.
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 Professor, I'm trying
Yeah.
to remember, how do you determine which way, like when it has to be below a line or above a line again?
There are 2 ways. That we looked at a couple lectures ago. Okay, so one way is to plug in a test point where you just take a random coordinate and you see which one works. And another way is if you imagine it like this. Another way is if you imagine it like this, you can know to go above or below or to the right or to the left. So going back to what we had, Here, if I were to say plug in a point, say plug in 0, 0, I would know that 0, I would get 2 times 0 plus 3 times 0 is less than or equal to 12, and this is true. So I know that the origin is in the solution, but the origin is below the line, right? So I know below the line is what solves that. Another thing would be if I were to solve for, say, the y, I would get, or solve for y, I would get y is less than or equal to, well, it would be 4 minus 2/3 x. And because my y is less than or equal to, this again means below. Because if you went back, here, you'd realize that here, less than or equal to means below. Okay, so either one of those methods, you'll figure out that, oh, I need to be below the blue line. Doing the same kind of thing is going to tell you where you have to be in regards to the red line. And you'd realize, for example, if I were to plug in 0, 0 into the red line, I would get 0 greater than or equal to 5, which is false, which means the origin is not in the red solution, which means the solution has to be above the red line, not below. Right? And again, I could have solved for y. My y would be greater than or equal to 5 minus x. Y greater than or equal to something is above the line, right? So a couple of ways you could do that. But yeah. So yeah, that was that one. D. Okay, and try to do it quicker. We're going to start 5.3 today, and pretty much for 5.3, you're not going to survive unless you know what we talked about in 5.1 and 2 very well. Like, it's going to be almost impossible to finish a problem. You're going to need to know how to solve systems of equations very quickly. You're going to need to know how to graph a picture like this very quickly. You're going to need to be able to identify the region very quickly, because you're going to have to be doing this while interpreting a word problem and answering a question. And these are the things you're going to need to be able to do in order to do that. So definitely review the last couple lectures, make sure you are solid on that stuff. The calculation part should not be something that's giving you any trouble, because there's going to come a point where we're going to have to apply interpretation to this and solving it word problem wise. So what region would do this?
Region 2.
Region 2, you'll see that you're above the blue, but below the red. Okay, so that's bounded. Okay, and now here's this one. Want you to notice that the equations x greater than or equal to 0 and y greater than or equal to 0 were removed, which means we're no longer confined to the first quadrant. The x and y axis will not be a boundary for us. So which one solves that?
Would that be 3?
So here?
Yes.
Anything else?
Could it also be 7? Oh, wait. Never mind, not 7.
I mean, that's not it. There are more places.
2. That's what I meant.
2. Right? And in this case, notice that this kind of goes off like that. And so bounded or unbounded?
Unbounded.
Unbounded. So that is how we can find solutions to systems of linear inequalities. And now we are going to do some cool things. Cool in the sense that, you know, very applied, very important things. Okay, go. Maybe want to move this guy out the way. Talk about you later. Okay, so now we're just going to start 5.3. We're going to go through an example. I'm going to teach you how to solve these problems in 5.3 by going through this example. And then I will leave you with some other examples, which are going to involve both the things that I asked you to look up as prereqs in section 1. So that is reading word problems and coming up with equations that describe the word problems, as well as doing this stuff that we've already been doing. Okay, so we're going to do linear programming, and we are going to do it by hand in 2 dimensions, because that way we can do the main thing that I wanted us to do, which is solve them graphically, solve them with pictures. And in higher dimensions, though, with more than 2 variables, we'll learn how to do that in Excel and Python. So yeah, let's start linear programming. This is where it's at, right? So 5.1, 5.2, we learned all that stuff just to be able to solve these kinds of problems. And they're very, very important kinds of problems to solve. I don't remember what journal it was in, but not too long ago, you know, people in industry had to vote. They did some sort of survey about, you know, what is the most useful mathematics, right? So a lot of people like, oh, I learned all this math in school, I never use it, right? So, but no, they ask these people, no, the people are actually using math in real life. What is the most useful mathematics, right? Obviously, probability and statistics will come up, right? Because even scientists, everyone uses probability and statistics, right? And so, but it turns out one of the most useful mathematical techniques was voted as the Simplex method. And the Simplex method is actually a method for solving linear programming problems. Being able to solve linear programming problems is a super duper important thing. It's used in real life all the time. A lot of times it's going to be used to solve your problems, whether you realize it or not. Linear programming is very, very important, very ubiquitous, all over the place, right? So you have these things in applied mathematics and where we use them in industry and stuff like that. So probability and statistics, differential equations, partial differential equations, linear programming, linear algebra, those are indispensable. Like you use them all the time, right? It's not just something that you learn in school and then you throw it away. Someone is using this all the time, right? And I mean, even artificial intelligence is a combination of those mathematics, right? That's essentially what it is. And artificial intelligence is a program that knows how to do those specific fields of mathematics in order to solve a problem. That's all it is. And so this is actually very, very important. So let's actually talk about what linear programming is, or more specifically, let's actually start by talking about what a linear programming is meant to describe, or what does solving a linear program help us to do. So let's start off with a definition. We will call it optimization. So this is a very broad field of mathematics. Optimization. Very broad field of mathematics. Pretty much, the definition is going to sound very vague when I say it, but I'll explain what it is when I say it. So this is the process, study, pursuit of making a situation as good as it can be. In the presence of constraints. Right? So constraints is basically restrictions. Okay? So sounds very vague, but let me basically tell you the gist of it. It's very, very broad, right? So it encompasses almost everything. Again, this is one of those things where it's used everywhere, and I mean everywhere. Everywhere. Okay, so optimization, what is that? Making something as good as it can be within constraints. What does that mean? Let's say, for example, you go into business. You're a business owner. You want to make stuff. You want to sell stuff. You want to make money, right? So you, as a business owner, you want to start growing your business. What do you want to do? You want to make a lot of money. You want to make a lot of profit, right? So to you, as the business owner, you might want to optimize something, make it as good as it can be in the sense of, I want to make my profit as big as it can be, right? I want it to be the best it can be, right? How much profit do you want? Infinite. I want infinite amount of profit. I want an infinite amount of money. And there's like, you might want that, but you can't actually get that because there are restrictions, right? To make an infinite amount of profit, you'd have to sell an infinite number of products, which means you have to hire an infinite number of employees. They have to be working an infinite number of hours. You need an infinite number of storage space. You need infinite, it's like you can't do it. There are restrictions. There are only 24 hours in a day. You can only hire so many employees. You can only have so much storage space. You can only have so much market share. There aren't an infinite amount of people to sell it to. There are literally only 7 billion people on the planet. You cannot go to infinity. There are restrictions. And so you're going to be like, okay, fine. How can I make my profit as large as it can be given all these restrictions? Given that I can only hire a certain amount of people for a certain amount of hours with a certain amount of storage space, that I can only get my product into a certain amount of storage, right? There are all these things that are going to prevent me from making my profit as big as it can be, right? So that's one example. If you figure out a way, given all your restrictions, to actually get the biggest profit, we say you've solved an optimization problem. You have made it as good as it can be within the constraints. And business and selling products is just one application. You always want to do this. You always want to get the best possible result based on the resources that you currently have access to, right? So it's a very broad thing. It's called optimization. Now, here's the thing about optimization. Mathematically, it actually turns out to be often turns out to be a very simple, quote unquote, idea. Mathematically, this often requires us to maximize or minimize a certain function called an objective function. It is our objective to optimize this function. And by optimize, what I mean is maximize or minimize. So going back to my example of profit, what does it mean to optimize profit? Maximize it. What does it mean to optimize cost? Minimize it. I don't want to pay a lot of cost. What does it mean to optimize your tax situation? Pay as least amount of taxes as possible, right? What does it mean to, like, a lot of times when you think, I want to make something as good as it can be, it turns out you can phrase that as, I want to make something as big as possible or as small as possible. And if I can track that thing with a function, I really want the output of that function to be as big as possible, which means to maximize it, or as small as possible, which means to minimize it. I want my profit function to be maximized. I want my cost function to be minimized. That way, which means my revenue function needs to be maximized and my cost function needs to be minimized. There's going to be a situation where you can describe what you want in terms of making something big as it can be, or making something small as it can be. This is called maximizing and minimizing. Okay, so leads us to the topic at hand, linear programming. A linear programming problem often abbreviate this LP, is an optimization problem which means our goal is to make something as good as it can be within some constraints where the objective function is linear. Right? So the objective function looks like a y equals mx plus b or something similar, right? And the constraints are linear inequalities. And inequalities. So that's why linear inequalities is important to us. So it turns out that there are a lot of situations in which to optimize something, you want to maximize or minimize some function. Many times that function ends up being linear, and the restrictions that you have are also linear. So you're selling a product that costs you $2 to make, and every time you sell it, you make $5. How would you find the profit? Well, my revenue would be 5 times X, where X is the number of products I make. My cost would be C equals 2 times X, where X is the number of products I make. And so my profit is going to be revenue minus cost. So my profit function P is going to be 5X minus 2X, which equals 3X, right? So P equals 3X is your objective function. That's a linear function, right? Which is a very simple revenue cost scenario, right? It cost me this much to make it, I make this much when I sell it. Your profit function is linear if you know those two facts, right? And then you now have, I can only hire people for 8 hours a day, making sure they get 1 hour break because otherwise it's illegal or whatever. So you have restrictions on how long you can make people work, how many employees you can hire. So you're like, the number of employees has to be less than or equal to this. The number of hours they can work is less than or equal to this, and blah, 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 right? So you can actually start to set up a problem based on this kind of scenario. You'll realize that you have to maximize or minimize a linear function, and there are linear inequalities constraints, right? Whenever you want to do that, this is called linear programming, and it is super useful, right? Used all the time, all over the place, whether you realize it or not. Okay, so that's a linear programming problem. So we will focus 2 main ways to solve these. Solve LPs. One, you can do graphically. This is our focus right now, and this is in 2 dimensions. You can do it in 3, but it becomes a lot harder. It becomes a lot harder very quickly in 2 dimensions. Like if it was higher than 2 dimensions, I would not do the graphical way, but 2 dimensions is what we're going to work on. 2, something using the simplex method, as it's called. Now, we won't need to know how to do this method, but when we learn to solve it in Excel, this will be the method that Excel would be using in the background. And we just need to know the commands that gets it to do it, right? So this is for all dimensions. Okay, so we are going to focus on the graphical one. So that being said, let's actually get to an example. So we are going to work through this example. I'm going to be explaining how to do the example as we work through it. Yeah. So for whatever reason, let's say this is what you know. I have a linear function that I want to maximize, z equals x plus 2y, right? That's a linear function. And I have these constraints. And you'll notice that all these constraints are linear inequalities. And as I was mentioning before, what's coming on the horizon is that we need to know how to read word problems and come up with these functions and then do this stuff, right? So these problems are very involved, which is why I'm saying you really need to go back over the past 2 lectures, make sure you understand everything, and you can do it very quickly, right? Because you're going to have to read a word problem, interpret it well enough to restate the problem in this form. And then once you do that, you're going to do all that other stuff that we've been learning in 5.1 and 5.2. So let's see what that would actually look like, right? So let's pretend I read a word problem and this is what I came up with, right? So now, step 1. Find the feasible region if it exists. Chances are in this class, if I ask you to do it, it's going to exist, right? We're not going to deal with that situation. But you should know, like in general, it's possible to not exist, right? Someone can come and say like, oh, I want to make the most amount of profits, but here's what I'm dealing with, and I want to make this much profit. And they can say, it's impossible, dude. Like there's no feasible region. It's not feasible to do that. Right? So yeah, sometimes there is no feasible region. Like the problem you want to solve isn't solvable. You have to do something else, right? But let's assume that we could find a feasible region, then you should, right? So immediately what you need to do is find the feasible region. This means you need to sketch so what this basically means is sketch the constraints, sketch the inequality constraints. And solve find the region that satisfies them. Okay, so that's what that's going to involve, which means we're going to focus on this guy for now, right? So we need to sketch all these guys. So remember, you sketch them by sketching the lines. So 2x plus y equals 22. So 2x plus y equals 22. So remember how you sketch these? Plug in one guy equals 0 at a time, solve for the other guy. So if I plug in y equals 0, I get x equals 11. If I plug in x equals 0, I get y equals 22. So that is going to look like, say, this. Uh, 2x plus y equals 22. I know that this is going to be 11. This is going to be 22. 2x plus y equals 22. Okay, yeah, that's the first one. Now we're going to get the other one, 13. X plus y equals 13. So let's do that here. So this one is x plus y equals 13. This means that this is 13. That is 13. Okay, what else? 2x plus 5y equals 50. If I plug in y equals 0, I get x equals 25. Plug in x equals 0, I get y equals 10. So I need 10 on the y-axis, 25 on the x-axis. Okay. So now I'm going to say, what is the feasible region? I want to be 2x plus y is less than or equal to 22, x plus y is less than or equal to 13, this is less than or equal to that. Well, I can solve for all the y's and I would get what less than or equal to, which means I want to be below all these lines. So I want to be to the right of that and above this because I have the x greater than or equal to 0 and the y greater than or equal to 0. As for all the lines, I need to be below all the lines. And so that I don't get mixed up, I want to also label all the lines. So this is going to be 2x plus 5y equals 50. Okay. Now, if I want to be below all the lines, well, that leaves me with this feasible region right here. And yeah, so you're going to have to do that relatively quickly. You're going to develop the problem, you're going to sketch this out, and that's what's going to happen. Now we go to step 2. Step 2 find all corner points, aka vertices. So what is a corner point or a vertex? These are where two or more constraints intersect on the boundary of the feasible region. So in this picture, what are my corner points? Well, this is going to be one of them. Let's call that V1. This is going to be another one, V2. This is going to be another one, V3. This is going to be another one, V4. This is going to be another one, V5. Okay, so that's what the next thing. So now we have to find all those guys. So we're going to go in and we're going to do that. V1. V1, that is easy. That's an x-intercept, right? Notice that it's 11, 0. This is 11, 0. It's an x-intercept. Okay, V2. For V2, notice that V2 is the intersection of x plus y equals 13 and 2x plus y equals 22. So for this one, I need to solve a system of equations. 2x plus y equals 22, x plus y equals 13. Right? So what can I do here? This is equation 1. That is equation, let me put this one up. Doesn't matter, but let me put this one here. X plus y equals 13, call that equation 1. 2x plus y equals 22, call that equation 2. What I can do is I can multiply equation 1 by -2. Oh, that was weird. And then I can say add them. Call this one equation 3. I can add them, take 3 plus 2, and then I would get -y equals -4. Okay. So my y equals 4. And so this means that my x must be equal to, well, 9, because, you know, my x plus y must be 13, my y is 4, my x must be 9. So that tells you that our V2 is 9, 4.
Wait, Professor, I'm confused where you got right after the third equation, the 1x minus 2 equals 3.
X minus 2 equals 3?
Yeah.
3 times. Oh, this is not x minus 2. This is, I took equation 1, I multiplied it by -2.
Oh, I see. Okay.
So this is multiply. I'm just writing out what I did. I multiply by -2 to get this new equation here, -2x minus 2y equals -26. And then I renamed that equation 3. And so now I can take equation 3 and equation 2 and I can add them. You'll see that stuff will cancel and I'd be left with that. So I get y equals 4. If my y equals 4, equation 1 would tell me that x equals 9. So that's my coordinate. So now V3, it's going to be the same process. I'm going to go see which two guys intersect, which is why labeling your lines are important. I mentioned that last time. Note that V3 is the intersection of x plus y equals 13 and 2x plus 5y equals 50. So same idea, call this equation 1, call that equation 2. Let's say multiply equation 1 by -2. I will call that equation 3. So that's -2x minus 2y equals -26. I'm going to take equation 3, add it to equation 2. The x's will die. I'd be left with 3y. And 50 minus 26 is 24. Solving for y, I get y equals 8. Since x plus y must be 13, if y equals 8, that means x equals 5. So this means my V3 is 5, 8. Moving on to V4. V4 is actually a y-intercept, so that's kind of easy, 0, 10. So y-intercept. V5. V5 is also easy, that's the origin. So now I've found all corner points. Notice that to find 2 of them, I need to really quickly solve 2 systems of equations, right? And this is just for the purpose of getting a more accurate diagram. That's all it is. Well, it's a little bit more than that, which I'll explain soon. So here, I'm just going to copy this picture, not because you have to draw 2 pictures, but because just for some clarity. What is this thing? Come on, stop misbehaving. Copy. Down here. Paste. Okay, so now I'm going to fill these guys in. So we know that this one is 11, 0. This one is 0, 0. This one is 0, 10. And V2 and V3 is 9, 4 and 5, 8. So this one is 9, 4. And this one is 5, 8. Okay, so now I found the corner points. That is step 2. Now, it turns out that there's a theorem, which we'll talk about next time, that says the following. A LP problem, let me write it differently. The optimal solution of an LP with a bounded, so this is why it's important to know, identify bounded from unbounded, feasible region occurs either at a corner point, which is why we need to find the corner points, of the feasible region, or on an edge on the boundary of the feasible region. The latter happening if 2 corner points along the edge both are optimal. So if I have 2 points that are optimal, then the entire edge in between them is also optimal, all points. So for example, I'm in this problem here. it turns out that the answer, the thing that's going to make this as good as it can be, is either going to be a corner point. So for example, it could be 9, 4 is going to be the best possible scenario, or it could be something like an edge in between like this and all points along this edge, in which case you would find that both 9, 4 and 5, 8 are the good solutions. Once you have 2 points that are a good solution, all points in between them along that edge is also an optimal solution, right? So that's what this theorem is telling us. The best possible scenario will occur at a corner point or at an edge in between 2 corner points, right? Which is interesting, but we'll talk about it later. But that tells us what step 3 is going to be. Test the corner points in the objective function. What does that mean? You will essentially make a table. You put in all the X values, all the Y values, and then your Z values. And there are 5 of them that are of concern here. There's the V1, V2, V3, V4, V5. You don't need to write this column. Also, I should point out, you don't need 2 diagrams. Just this one. So up here, it's the same diagram. It's just that I didn't label the coordinates yet. Whereas here, I have the coordinates labeled. So you just want a fully labeled diagram. So you only need 1 of these guys. Now, what we're going to do is we're going to plug in all those points. So what do we have? V1 is 11, 0. Then I have 9, 4. 11, 0, 9, 4. 5, 8, 0, 10, 0, 0. And this was X plus 2Y, if I recall correctly. Yes. Okay, so I want you to notice we ignored the objective until this point. Everything we've been doing up to this point, we're doing with the constraints. So you don't even look at the objective until you get to this stage, step 3. In which case now, you're just going to plug in the X and Y values of the corner points into that function. So plug in X equals 11, Y equals 0 into X plus 2Y, I would get 11. If X equals 9 and Y equals 4, I would get 9 plus 8, which is 17. If X equals 5 and Y equals 8, 2, 8, 16 plus 5, 21. X equals 0, Y equals 10, that would give me 20. If X equals 0 and Y equals 0, that would give me 0. Now what I do is I want to maximize it, right? That was the goal. So you now pick out the maximum. That's this line right here. Maximum set, right? That's the best you can do in this scenario. Make X 5, Y equals 8. Your biggest possible output is 21. Can be whatever you want. So you can't be like, I want the output to be 50. It's impossible, dude. Not with the constraints you have, right? So you could have your X is the number of employees and your Y is the number of hours per day they have to work. And the 21, the Z is like your profit. They can say the maximum profit you can make per day is $21. To accomplish this, you need 5 employees working for 8 hours a day. Like someone will be able to tell you that as the answer if you describe to them your situation. And a lot of times, linear programming is how they figure out that answer. Lastly, is to just state your answer. and we're done. Step 4, state your answer. So here I would say the optimal Z value is 21. This occurs at xy equals 5, 8. The situation is now optimized. That's the best we can do. You will not be able to find a value. And if you don't believe me, go home, pick 100 other points than this that fall inside this region. I dare you. None of them will give you a value higher than 21. 21 is the biggest you can get here. And that's essentially optimization, linear programming. Now, what I'll do is I'll just leave these examples for you guys to try for next time. And I do encourage you to try them for next time, where you have another level higher. You're gonna have to read the word problems, interpret them, and then do everything that I just told you to do. So I'll leave these in the notes, and we will pick up there tomorrow. So for now, we will stop there. Thank you for your time and attention. Hope you guys have a good rest of your day, and I'll see you in the next one.